Hi, everyone. Okay, so last time we got stuck into paramagnetism, and now we're going to move on into the Ising model. We'll get through the Ising model, and we might get a little bit into the next topic as well. We'll see how we go. Ising model is like, on the one hand, it seems like a real specific example of the things that we've been doing already. And you're like, why do we have to do yet another example? And the answer is because this one pops up in physics all the time. Many, many places. It's been applied to many parts of physics, and everything from understanding semiconductors all the way up to the flocking of birds. Consider the Hamiltonian, and this is what it looks like. I wrote it down last time. It's the sum over pairs of spins, some number j, which is usually just taken as being positive, but it doesn't have to be. And I'm just going to put jzi times sigma zj. So we'll just have two sigmas, and then ij is sum over pairs. I'll explain this in a bit more in a second. Pairs of spins. Nearest neighbor spins, and j is greater than 0 is just some energy scale. So you can have j less than 0 as well, but let's just stick with j greater than 0 for today. So j greater than 0 is for ferromagnets. Okay, so let's have a look at what this looks like in 1D. One dimension, 1D. We've got a large, long list of spins, and then you start going spin up, spin down, spin down, spin up, spin down, spin down, spin up, spin up, spin down, spin down. So we want to know, how do these spins, what do these spins do? They're all going to be up, they're all going to be down, what's going to happen? So before we get into the mathematics of it, it's worth always thinking about the physics. What do we expect to happen here? Firstly, you'll notice that for any individual spin, there's no preference to be spin up or spin down. Yeah? In that Hamiltonian, there's no particular preference. However, if the spins to the left or to the right are spin up and spin down, that will affect whether you want to be spin up, whether a spin wants to be spin up and spin down. So it's a little bit different. What do we expect to happen? Firstly, at high temperature, what do you expect to happen? Completely random. I had to expect complete disorder. The complete disorder. What would be the energy of complete disorder if I had like a Hamiltonian like this one, where if two spins are aligned, it's minus j, and if they're anti-aligned, it's plus j. If I have complete disorder, what's the energy that corresponds to that from this Hamiltonian? Excellent. E equals 0. Average energy. Okay, great. Another way of saying that would be to say that the correlation between, did I talk about correlation last time? I don't remember. No, I didn't. Come back to that then on a different point. Forget about that one. Okay, what about at low temperature? What about at T equals 0? What do I expect to happen at T equals 0? All the spins to be aligned. Up or down? There is no magnetic field. It's actually a degenerate ground state. Yeah? Degenerate ground state. They're either all up or they're all down. If you break that degeneracy, if you put in a magnetic field, yeah, even on one spin, then at temperature 0, you've now broken that degeneracy by an infinite amount. E to the minus beta j becomes e to the minus infinity j. So as t goes to 0, beta goes to infinity. So you get a very large gap. Yeah. So t equals 0, you expect all the spins to line either up or down. Don't know which. A tiny magnetic field will break its symmetry since the Boltzmann distribution favors the lowest state. Good. So that's what we expect. So what we're going to need to do is to find a partition function for this. So let's work out the partition function, because that's what we do these days. Partition function. Remember, partition function, we sum up over all possible configurations. Or microstates is another way of saying it. The energy, e to the power of beta, and the energy is j times the sum over all of the pairs, ij, sigma zi, sigma zj. So we've got a sum in the sum. And it's pretty clear that this looks very difficult. This looks very difficult because it looks difficult. So for any given configuration, like this is one particular configuration of the spins, I will need to go along here and have a look at all pairs. And I'll have to go, that's a minus j. These ones are opposite direction, so it's a plus j. This is a minus, this is a plus, and so on and so forth. Yes. 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 Only neighbors. Only nearest neighbors. Nearest neighbors means these ones will have an energy of plus j because they're opposite directions. These two would have an energy contribution of minus j because they're in the same direction. Yeah? Now I have to sum up over all pairs. Yeah, all nearest neighbors. All nearest neighbor pairs. So think about doing this, and you might come to the conclusion that this is not very easy, because for every configuration you have to work out like whether each pair is having a positive or a minus sign, and it seems like this kind of sum seems very, very difficult. There is a trick to this, and the trick is to consider those pairs themselves as the particles. So the trick is that we say consider pairs of spins. One second. So it'll be sigma zi, sigma zi plus 1. Yeah? And that's either going to be plus or minus 1 for every pair. Yes. And so, yeah, it's just the left and the right neighbor. So that is nearest neighbor. Nearest neighbors. Nearest neighbor means that for this spin, if this is the spin, there's a new color. This is the spin I, then J could either be I plus 1. Oh, that looks terrible. Sometimes it's just the writing on this thing. J equals I plus 1 or J equals I minus 1. That's my two options for that particular spin. Yeah. So just the nearest neighbors, just the next door neighbor. Yeah. Great question. Is there an edge? You can either think about this as being they're in a ring, cyclic boundary conditions, or you can put an edge in. If you put in an edge, you might think, I now need to take the edge into account. Go for it. Enjoy doing that. As n, the number of spins goes to infinity, and remember, n is large because we're in statistical mechanics land, that edge doesn't matter anymore. It'll be like some small delta on the partition function, some small delta on the energy, and as a proportion of the total energy, it will be negligible. This is why statistical mechanics always works. So if you don't like that, by all means, do cyclic boundary conditions. Yes. Yeah, n minus 1 pairs or n. Like I said just 1 second ago, I don't care which you choose. N is large. 10 to the 20 is equal to 10 to the 20 minus 1. Mathematically, identical. Cannot be separated. So consider pairs of spins. So again, up, up, down, down, up, down, up, up, down, so on and so forth. Let's have a look at the pairs. What are the pairs doing? So here we have a situation where we have the representation of spins, but let's just look at the representation of pairs. Representation of pairs, and I've defined this thing Ti by definition. I've said it's I and I plus 1. So here, Ti is equal to plus 1. This one and the next one are opposite directions. Same direction, opposite direction, opposite direction, opposite direction, same direction, opposite direction. Get it? Cool. So now I just need to worry about whether they're the same direction or opposite direction. These T's are independent. Not in the sense of if I change one of the spins, it only affects one of the T's. They're independent in the sense of if I make a sum over all possible configurations of spins, it's exactly the same as making a sum over all possible configurations of T's, of pairs. Yeah? So wherever I am, like if I'm writing one of these down, I'm going plus, minus, plus, plus, minus, minus. I can make the next T whatever I want. I can make it the same or different. Yeah? In that sense, they're independent. Yeah, so if I'm making up a set of spins or making up a set of pairs, it's actually identical. Yeah, they map one to the other. So these Ti pairs are independent. So now my Z can be written as sorry, I'll write my energy instead first. My energy, H, equals minus J sum over the T, or sum over the pairs I should say. Okay, sum of the pairs I, e to the minus beta Ti. Comparing it. Oh, I've already put the minus sign. Geez, I'm a dummy. That's not what I meant at all. Ti. Have I got the signs right? If they're the same, they're aligned, that's a plus, and then I get a minus sign out the front. So it's correct. Okay. So that's H. Right, not beta, H. Shouldn't get this thing right. So that's the energy. So that is exactly the same energy as I've got up here. Same energy. Right? So I've just replaced this sum over pairs here with sum over TIs. Okay. So once I've got that, now I can write down the partition function. Z is equal to sum over all of the configurations of e to the minus beta j, j is negative, sum over I of ti. Okay. And they're all independent. And it's a configuration. Have we done something like this before? Yes. In fact, it's exactly what we've done before. If we have independent spins, then I can write this as Z1 to the power of n. Yeah? Always. So because if you want to do it formally, you can. Because these are independent of each other, non-interacting, I can write it as Z1 to the power of n. What's Z1? It's just the sum ti equals -1 or +1. That's my two options. E to the beta j t1. I should write t1, not ti, because we're just doing one specific example. T1 to the power of n. And that's just e to the beta j plus e to the minus beta j to the power of n. And that's 2 cosh beta j to the power of n. So that's my partition function. So by mapping from the spins to the pairs of spins, I find I get an easy way of getting the partition function. Once I've got the partition function, I have everything I need, right? So in other words, there's a duality. By changing the variables from the spins to the pairs of spins, I am mapping the coupled system, the coupled spin system, to an uncoupled pair system. Yeah? So it makes it a lot easier. So once I know that I'm just summing over the pairs, makes my life a lot easier. It's a little trick. And now I've got the partition function. Once I've got the partition function, I'm now back to the paramagnetic case that we did last week. The only thing I would want to add now is to look at the correlation between spins. Yes. They're independent on the sense of you can build a system with arbitrary TIs in that sense. Yeah. And the energy is the sum of those TIs. And each TI does not affect any of the other ones in terms of the energy. Yeah. You're thinking, oh, if I flip a switch, I change 2 TIs. I don't care, because we're not flipping a spin. What we're doing is we're summing over all possible configurations. We are summing over all possible configurations. In each configuration, the energy is a sum over those TI. Yeah, a simple sum over those TI. This one. That's the energy. Really simple. Yeah, they're independent. They don't affect the energy in pairs. They affect the energy separately, and they affect the configuration separately. Yeah. Do you see how you can write down any any configuration can be written down as a sum over T's, and conversely, any set of T's will correspond to a configuration. So that's the sense. Edge effects might be an issue. I want to have this plus 1 more degree of freedom because I've got edges. No, so this is the first one, up or down. That one's unpaired if I've got edges. So now I need to have plus an extra degree of freedom, plus 1 more. But I don't care about that one, right? Because like I said before, it's like, it's a tiny effect. If you want to do it, do it. This is the canonical distribution. Where do you think this beta comes from? This Z that I've written down is for the canonical distribution. We are in the canonical distribution. We have heat. Canonical distribution just means I have a fixed number of particles and heat. Canonical distribution. Okay. So next thing, an interesting question that I might want to ask is about correlations between spins. I'll explain what I mean in 1 second. So, what's the average value of T? What is the average value of T for a particular system? You guys can all do this now, right? You've got the partition function. So in principle, you could work out the average value of T. Let's do it. It's the derivative, your beta. Right? How can I see that? Have a look at this. Have a look at this guy, and I say, here is my partition function. Here it is in terms of the T. And so if I take the derivative of this thing with respect to the beta, I bring down the T. This is exactly what we did before. So I get tan H beta J. That is the expectation value of T. This expectation value of T, because T is just definitionally, T is given at the top here, it's sigma Zi plus 1. The average value of that is called the correlation between sigma I plus 1. That is the correlation between two spins. Yeah? So that's the correlation between two spins that are neighbors. Sorry? Here's my partition function Z. If I take the derivative of the logarithm of this, is that what you're asking? Take the derivative of this thing. I can't do it. Oh man. It cannot expect me to do. Okay, let's work out. J. So it's N. Can't do it. It's too hard. Oh, I didn't understand the question. Different question. Different question. Where did T equals this thing come from? Why? Because the expectation value of T is equal to the sum over all of the configurations of the probability of that configuration times T for that case, yeah? And so that's equal to equals so if I take the Z and I take the derivative with respect to beta, I'm bringing down this Ti here. Is there a minus sign missing? Maybe there's a minus sign missing. Doesn't matter. Sorry? Yeah, there should be, maybe there should be a J. That would cancel out in the logarithmic derivative, I think, won't it? Oh, no, beta J. I need the beta J. Okay, I need the beta J. You have to do, I haven't got the details. Please do this one at home. It's you actually ask me about factors of J now, which I understand and I appreciate. You need to get those correct. Please do this at home. The average value of T is going to be definitionally the probability of being in a state times the value itself, right? This is definitionally true. Yeah, has to be. That's the definition of the average. Yeah, probability times the value. So if I've missed out factor of J or something, it doesn't matter. It comes out to this anyway. Yeah, actually, not energy average, it's sum over probabilities. The definition of a probability is that, yeah, is yeah, and in this case, it's the same. So I might be out by factor of J. Like I said, I might be out by factor of J. There's a factor of J somewhere. But here you've got, this answers your question. This T is very simple and it's quickly related to energy. So if I want to get the average T or the average energy, it's the same thing up to a factor of J. Can you see that? Yeah. The energies, this is some of the T's with a factor of J. I've missed a factor of J. I apologize, but I can't find it right now. I've got too much to do today. My life is hard. Woe is me. Yeah. So I'm correct within a factor of J. If I miss a factor of J, I'll live with it. So the next thing we want to know is what about correlations between spins at different distances from each other? Okay, so I've got, let's say I've got a list like this. I've got, you know, a spin here. Here's sigma I, and here's sigma, oops, some other spin here. Sigma I plus n. So these guys are not nearest neighbors now, but they're separated by a whole bunch of spins. And the question is then, what is the correlation between these two? What is the correlation between these two? And I bring this one up because this will be important later on, I think, if I remember correctly. This one becomes important. How do I calculate this correlation? Well, again, I can use a trick. I can use a trick because I've already worked out the correlation between two. So I can just keep going. And how I can keep going is like this. If I take this one and put in sigma I plus 1, and sigma I plus 1 again. Now, sigma I plus 1 is either going to be plus 1 or minus 1. If I put it in twice, it's that squared, so it's 1. In other words, I can put in as many 1s as I like. Now I'm going to put in I plus 2. And I'm going to keep going until I get to sigma I plus n. So all I've done is multiply it by a bunch of 1s. And then if I look at this thing, I'll go, I know what this is. This is Ti. The next part is Ti plus 1. Next term is Ti plus 2. Yeah, all the way up to Ti plus n minus 1. That's my last one. And so this correlation is nothing but tan beta j to the power of n minus 1. So it's a correlation to the expectation value Ti n minus 1 times. So as this n becomes large, as n becomes large, right, then the correlation, there are lots and lots of correlations. There are, sorry, tan beta j is some number between minus 1 and plus 1. So it's some number that's smaller than 1 to the power of n minus 1. So the correlation goes to 0, as it should. Yeah? So for any finite temperature as well, right, there has to be some kind of loss, because tan beta j can't go to 1 exactly. It can go close to 1, but it can't exactly be 1. This should be tan h, by the way, obviously, tan h. Tan h goes between minus 1 and plus 1. So because it's a number between minus 1 plus 1, not exactly plus 1, then the correlations over large distances will eventually have to go to 0. Okay. Except for perfect fidelity, which might happen at exactly 0. All right. So far, that's complicated, but that's not the Ising model yet. That was just like a little pointing out that we can map the Ising model without a magnetic field back to paramagnetic systems that we did last week. The next thing we want to do is add an external field. And then we have like the full Ising model. Sum over the pairs, same. But now for each one of them, I've got a energy mu b, sigma I. Okay. This one is extremely difficult to solve. It can be solved for one dimension, but I'm not going to do that because I don't think doing that kind of mathematics is too much fun. And I don't think we learn much from it. Instead, what we're going to go is to higher dimensions and we're going to cheat. The reason why we're doing this is because it's going to lead to something which we haven't seen for a long, long time since Paul's part of the course. So without getting too excited, we might see some phase transitions. So I don't want to solve this one exactly, but I will try and solve it as best I can. We're going to do, firstly, start by solving this in the mean field approximation. So what does pairs look like in higher dimensions? For example, 2D or 3D, 4D, 5D, and so on. Yeah. J is just a constant that couples, yeah, it's an energy constant that couples the, yeah? It's how much energy you get for having the two spins aligned or not aligned. So high dimensions. You've got some spin. Let's say we have like a cubic lattice, okay? You've got some spin here, and then you've got all of its neighbors in the plane, and then maybe out of plane as well. Yeah? How many neighbors do I have? 6. 6 neighbors. So we'll write D neighbors. Before we had 2 neighbors, one in front and the one behind in one dimension. Now we've got more neighbors because we're in higher dimensions. So, for example, you might have your spin I here, and then all of the ones that I've shown are J's. There's 6 of them. Yeah. Alternatively, you might be thinking, okay, I'm in 2 dimensions, but it's a different kind of lattice. So for a square lattice, how many pairs would I have? How many neighbors would each one have? 4 for a square lattice. What about for a hexagonal lattice, a triangular lattice? 6. Yeah. So let me try and draw a triangular lattice. And so on. So this case, you've got D equals 6 again. Yeah, this guy here has 6 neighbors. Okay, what was your question? Nothing. Okay, so 6 neighbors. So you can see that you're not always going to have the same number of neighbors, but you've got D. And the idea is that this is going to work. What I'm about to teach you is something called mean field. And mean field works when D is bigger than 1. How much bigger? Much bigger. What's a big number? Four is much bigger than 1 today. Good news, everybody. So how do we do it? The energy of the system is going to be the sum of the energies of the individual spins. And for one spin, if I look at just the ith spin, I've got minus j, the sum over ij, where I is neighbors, sigma I, sorry, I should put in the z's. I always forget that one. Sigma z I, sigma z j. Let me leave out the magnetic field for the time being. We'll come back to the magnetic field. By going through the mean field, we can get that. So for one of the spins, I can write minus j, sigma z I is the same for all of them. Yeah, have to sum over all of the j neighbors. Sum over the neighbors, sigma z j. Yeah. How many neighbors are there? D. I've got D of them, and they have an average spin. Yeah. So far I haven't done anything. I've just done some definition. And the definition I write is sigma bar is average spin of neighbors. Good so far? So D sigma equals the sum over the neighbors. Yep, just a definition. Okay, cool. Now let's work out the partition function for that one spin. For the ith spin, Zi equals either that spin is going to be up or down. I've got e to the minus beta dj sigma bar, or it's spin in the other direction. Yeah, my two options. Sigma z here is either +1 or -1. If it's +1, I get the first term. If it's -1, I get the second term. That's it. So I can say that this thing is equal to 2 cosh beta dj sigma bar. Because we end up using these coshes, you end up, when you've got like a 2-state system, and it's that to the power of something, and they're all independent. You always end up with like coshers. So that's why getting used to coshers and shines and tans is a good idea. This makes life a little bit easier. But again, in exam or whatever, if you just want to leave it as exponentials, I'm fine with that. So that's the partition function for the one neighbor. And so what's the expectation value for sigma I? I would say it's the sum of sigma I equals plus or minus 1. Here I am doing in detail what I was supposed to be doing last time that I just skipped the details. Here's the probability. Yeah. So that's the expectation value. And if I work out what that is, it's equal to, for sigma equals plus 1 over z e to the minus beta dj sigma bar. And then I've got to add the minus 1 case, but now I get a sigma I equals minus 1 times 1 over z e to the plus beta dj sigma bar. Yeah. What's this guy? This guy is called tan H. Cool. Tan H. So that gives me the expectation value of sigma. The expectation value. Very good. Yeah.
So you said the sigma bar average for the babies. If you needed to divide over, or is D4 or D like 5?
So here's D equals 6, right? And D equals 4 for a square lattice or whatever. Yeah. So so I guess this definition here, I've got a sum over things equals D times the average. Yeah, because I'll be summing over 4 things. If D equals 4 and I'm summing over 4 things here, then 4 times the average spin will be the sum over those on average. Correct. Oh, really? You're getting confused about the D being differential? Oh, man. I's are not always square roots of -1 and D's are not always differentials. Yeah. No, I have not forgotten that. I can put in this, that's Zi, that's Zi. Why am I doing Zi? It's because they're all independent. It's equal to 1 over Z. Z is e to the minus beta. You got it? 2 cosh beta dj sigma, 2 sine beta dj sigma. Okay. Okay. So I've got an expectation value for the ith spin. In terms of beta, the temperature, inverse temperature, D, the number of sites that are nearest neighbors, J, this energy scale, and sigma bar, the average of all the other spins except for this one that are nearest neighbors, yeah? For a self-consistent field, and this is what mean field comes to, or self-consistent field. For a self-consistent field, this sigma here, the average here, should be equal to this sigma bar. Why? Because each spin is in part of the nearest neighbors of its nearest neighbors. My neighbor's neighbors is me. Yeah? So if this is going to be true for all of the spins, then all of the spins should have the same average value, sigma bar. Yeah? So if they all have the same average value, That's the requirement for self-consistency. So I can say then that the average value is equal to tan H of beta dj sigma bar. Okay. That's a transcendental equation which does not have an exact simple solution, but I can graph it very easily. It's time for us to remind ourselves what tan H looks like. So we're going to do a graphical solution of this thing. Here is sigma bar. That's 0. I need +1 and -1. Here is the line sigma bar. And here is my attempt at tan H. It's supposed to be symmetric. This is tan H of beta dj sigma bar. And importantly, there is a slope here at 0. If you work out what that slope is, it's beta dj slope. Okay. Good. So at what point is this equation sigma, where is this satisfied? So equation 1, this equation, star is satisfied at 3 places. Where are they? Here, here, and here. So at these 3 points, I can satisfy this equation. If I have beta dj greater than 1. So we satisfy in 3 places if beta dj is greater than 1. I will not get into the full stability of the solution here, but I would like to point out that the 2 non-trivial, the non-zero solutions are stable, and the one at 0 is not stable in the case that beta dj is greater than 1. Physically, I know why that is. Yeah, physically it becomes unstable because that's an average expectation value of 0, and I know that that's not going to be stable because as soon as they start to like relax into one of the other ones, they'll attract to being all in the same spin states. But on average, if beta dj is greater than 1, then there'll be those 3 solutions. If beta dj is less than or equal to 1, then there's only one solution. It's the only solution, and it's stable. Yeah, because in that case, if that was the case, if this is less than 1, then this thing here would look like this, and it wouldn't cross that green line. Yeah. Okay. So when does beta dj become greater than 1? That means that kt is less than dj. Beta is 1 over kt. So it's the same condition. In other words, at low temperature, kt is less than dj. At low temperature, then you have ordering, if you're above that threshold, it's disordered. What does that look like? I can actually do another plot, and the plot would look like this: is temperature, and put KT there, and I'll put average value of spin. What happens if we're at, actually, I would just put temperature here because otherwise it'd be confusing. Temperature. Some point here, which is the threshold. This threshold happens at temperature critical equals dj over k Boltzmann. If we're above that, then we're on this line. The average spin is equal to 0. Why? Because if we're above that, then you can't have that tan H crossing that green line. If we're below it, then we can. If we're below it, we have two solutions. So you have this bifurcation like this. So below TC, there are two solutions, the positive solution and the negative solution, right, which are exactly equivalent. And you have a magnetization which is non-zero, an average magnetization. If you're close to 0 temperature, then you can see that you would have almost complete magnetization. Can I see that from this graph? Yes, I can. If we're at really low temperature, then this thing here becomes very, very sharp and will intersect very, very close to 1 up here. Yeah? Okay. So this is a phase diagram, and what we've got here is a phase transition at this TC. Yeah? Where have you seen a phase transition already in this course? Van der Waals. Yep. Yep. So Van der Waals was one example of phase transition. This is the second one that you get to see in this course. Phase transition here between ordering and disordering of the Ising model. What I haven't done yet is put in a magnetic field. Yeah. But I should write down ordering for T less than TC. And if it's not, then it's disordered. Okay. I'm going for time. All right, so we're around 1 o'clock. Great. If you add a magnetic field, let's put in the magnetic field now. Add field back in. Then energy is going to be equal to, for the ith one, it's minus dj sigma I sigma bar, just like what we had before. And now we've got minus mu b b sigma I. That would be the energy for the ith one, right? So it's the first part that was the same, and the second part we've got magnetic field. So we can write this as just minus sigma I, and now I've got dj plus mu, sorry, dj sigma bar minus plus mu b b. Cool. So if I go through the whole thing again and solve it, I will find self-consistent. So it's exactly the same. Keep going, do all the things, solution that you did before, except just with that extra term. It all comes out exactly the same. And you find that the average value of sigma I is tan H of beta dj sigma plus beta mu b. And that should be equal to itself for the self-consistent field. So it's exactly the same, but now we've just added this extra term. What does that extra term do? Which way? Yeah, exactly. So all you do is you shift the tan H function a little bit. So now it does this. It's my attempt to draw again. The difference now is that regardless of what sigma, what beta dj is, there'll always be a non-trivial solution. Great. Yeah. So even if that magnetism is really, really small, if I just shift it off zero a little bit, it means that there is a non-zero solution to sigma bar. Yeah. So you guys can play with that yourselves. You can tool it up on Mathematica. I'll take questions now about this part. If anyone wants to ask any questions about Ising model, I think going through this self-consistent field methodology gives us the advantage that we don't need to do really complicated hard mathematics. We just need to know what the shape of the tan function is. Yeah. This one is stable, yes. Stability is a more difficult thing. Maybe I'll write a question about stability for the assignment. It's a good idea. That's a great idea. Thank you for that suggestion. In this case, there would only be one solution the way I've drawn it. Yeah, because again, that whether there's more than one solution depends on like the ratio of BDJ versus beta mu B now. Yeah. So that's right. So basically what you're doing is you're taking this guy here and you're moving it a little bit to the left, that curve. If you move it a little bit, you might get 3 solutions. You might get 2 solutions. You might only have 1 solution. Yeah. And the stability of all of those is not exactly obvious. That rightmost one will be stable, but there may not be a negative energy solution. There'll always be that right-hand solution. Yeah. Yes. The question is, if you've got this stable state, is this all the spins aligning to the magnetic field? Is that what you mean? Yes, except that we have temperature. Temperature means that you're penalized for having exact ordering because there's only one way of doing that. But there are many ways of having, if one of the spins is pointing the wrong way, I've got n more ways of arranging that than if I have them all aligned the same way. Yeah. This is the foundation of statistical mechanics, that there are more ways of having disorder than there are order, and that needs it to be more likely to be. Yeah. So it's more likely to have more disorder. So it's a trade-off between order and disorder. Here, what we have is that little shift means that there's always going to be the possibility for almost complete ordering. Yeah. What's the physically sound solution in this case? So that you can do a full stability analysis. Okay. I've aligned the magnetic field in the positive Z direction. Yeah. It's hot. Do you expect that there'll be more spins aligned with the magnetic field or against the magnetic field? Aligned with it. So do I expect the average spin to be positive or negative? Which is going to be the stable solution? Positive. So without doing any mathematics, by thinking and using our noggins, we know what the correct solution is going to be, right? Okay, now we don't have to do a stability analysis anymore, right? Let's assume that there is another solution here, which is, let's say there was another solution where it looked like yeah. So now I've got, sorry, my bad. That should not have been drawn like that. Try again. That's how I meant to draw it. Here I've got a situation where I've got 1, 2, no, sorry, 1, 2, 3 solutions. Yeah, red and the green cross 3 times. 1, 2, 3. Which is the correct solution? One on the right. The other 2 formally exist. Do you expect those to be stable or unstable? Unstable. Why? Because it's stupid and it goes against my physical intuition of what's going to happen here. Okay. Am I sure about that? No. Can I do a test to find out whether it's actually stable? Yes. What will I find out from that test? I'll find out that I'm not an idiot, that I understand physics, even if the mathematics is telling me something different. Yeah. The other case was stable. This case, this stable, and this is stable. What's the difference between these 2 cases? There's no magnetic field. Up is just as good as down. You can't tell me which way to point. Yeah, that's the difference. Okay. Maybe this one's stable. Who knows? Maybe I'm wrong. Yeah. I think this one's probably stable. A stable solution. Well, I think in this case, right, with these 3, right, let's use our noggins. We know that there's the one that's aligned. Yeah. Let's say that I have them all aligned. I'm at relatively low temperature, so that I'm in this regime here. Yeah. Remember that this is beta DJ, right? So this is like, if I make low temperature, it looks more and more like this step function here. Yeah. So I'm at low temperature and I've got magnetic fields and everything's aligned with my magnetic fields. Yeah. And they're all aligned. And now I change the magnetic field from up to down. What happens? This is called hysteresis. Would I expect that they all immediately flip? No, it does not happen. What happens instead is that you have a sort of semi-stable solution there. Yeah. Yeah, and like, what's the mechanism for changing it? And is there a cost to that change? Or is it like, yeah, now you're into the details, but like stable or unstable is clear. You can work it out. Is it stable or is it unstable? In other words, if I have if one of them flips, do they all start going, oh man, I'm not happy here, I'm going to do something else? Or do they just keep doing the thing? Yeah. Does that answer your question? I don't know if it does. It does. Okay, good. Yeah. So stable and unstable is not obvious, but like the result here in terms of physics is crystal clear. Let's take a little break there. And I will say that that's enough for canonical distribution for now. We're going to actually, I've got probably another, well, I've got 50 minutes. I'll take a 5-minute break now. Give me half an hour to get started on the next part. Next topic, which is grand canonical distribution.